All right, let's do a little quick one here and talk about formula mass. You kinda should already know this because we've talked about atomic mass and that kind of stuff, and they all really just go together. Um, what we're talking about when we say formula mass, this is the mass of a chemical formula. It doesn't matter what the formula is, uh, an ion, a compound, an ionic compound, a molecular compound, whatever. Uh, if it's got a formula, you can figure out the mass of it. Um, Officially, our definition is going to be the average mass of that formula with units of AMU. Remember, AMU is for formula mass and for atomic mass. So we have those two different ideas there. And the way we're going to figure this out is we're going to do with the sum of all of the masses of all of the atoms in the formula. Okay, I'm going to work this potassium sulfate example for us. We're going to need some periodic table, so there's that. I've trimmed it down so it fits, but you should be able to figure out where stuff is. Where's my mouse? There we go. Okay. Sorry. All right, so we also want to be able to show our work when we do this, so I'm going to write this out kind of long ways, and we're just going to see how it goes. This is how I'd work through this. Okay, so we want AMUs. Okay, good. So we have two potassium. Come back here, man. Two potassiums. Each potassium is 39.098 AMUs. This is going to give us a number. Um, we have one sulfur. You don't just have to show the one. I'm doing it for completion here. 32.065 AMU. That'll equal something. And then we have 4 oxygens. So that's 4 times 15.998 AMU. All right, so we're going to multiply these out and write them down. 2 times 39.098 is 78.196 AMU. Remember, this mass is exact and not exact. The mass is data, so the significant figures matter there. The number we're multiplying by is exact, so we don't have to worry about it there. This is times 1, so it's just 32.065. And then we're going to do 4 times 15.998 and get 63.992 AMU. All right, that's step 1. And we're going to add all this together. So we're going to take all this and add it. Yeah, that's how I show my work. It's kind of that, but you can do the same idea. All right, so 71.196 plus 32.065 plus 63.992 is 174.253. Okay, AMU. All right, so what I really want us to drill in here is to say that anytime we're dealing with formula mass, our units are AMU. So this is atomic mass and formula mass. We're going to do AMU. Remember, AMU is atomic mass unit. Cool. All right, let's see what's next. Okay, molar mass. This is the same idea. We've talked about molar mass in terms of atoms. Now we're talking about molar mass in terms of compounds and formulas, but it's the same idea. Remember, we said molar mass is the mass of 1 mole of thing. This has units of grams per mole. And just like we saw with atomic mass, the formula mass is the same idea as the molar mass. So I'll pop this up here. All right, so we just figured out that is that really what we figured out? Yes. Okay, that this is our formula mass of K2SO4, so our molar mass has the same unit. So this is the same number as formula mass, but it's going to have grams, that's a G, per mole for the units. Okay, now let's do this example I've got here. How many grams are there if we have 8.33 moles of potassium sulfate, right? Molar mass is anytime we want to get between grams and moles in either direction. So here we have moles. We're going to figure out some grams. So this is 8.33 moles. You could put the formula on there. I'm going to go ahead and say that we're not going to need it because we're keeping it as potassium sulfate throughout the whole problem. We're going to see some stuff in a minute here about how we'll need to add the formulas on there so that we can do it. There we go. 174.253 grams. All right. I usually give you molar mass unless I want molar mass to be the answer for something. If you're working something and they don't give you molar mass, you know how to do it, right? You can just add it up from the periodic table. So essentially, we're going to take 8.33 and multiply that by our atomic mass, and we're going to find out that we have a lot of potassium sulfate. We have 145152749 grams. Okay. 3 significant figures means we have 1,450 grams. That is very sloppy, but you know what I mean. I said it. There we go. Okay. Let's do something else. Yes, Avogadro's number. We remember Avogadro's number. Here's Avogadro's number. Here, right? 6.022 times 10 to the 23rd. We should know that. Remember, that's just for counting things back and forth. We can use Avogadro's number to count, but just remember that Avogadro's number relates to moles. Avogadro is related to moles, not to grams. So if you're given grams and you're counting individual things, or if you have a number of individual things and you're trying to get to grams, molar mass has to go in the middle so we can string those guys together. All right, what do we got? All right, so how many molecules are there in that many grams of methane? 35.88 grams of methane. Of course, I wrote on where this is going to show up, so let me erase this moles. Avogadro relates to moles. There we go. All right, so there's our methane. Remember, you should know methane is CH4. Here I've given us molar mass, so we're good to go. We have grams. We're looking for numbers of molecules, so we're going to have to go grams to moles to molecules. So we're going to have an extra step in here than we did before. All right, so 35.88 grams. I don't know why I'm having issue. Okay, here we go. 35.88 grams. We know 1 mole of methane is going to give us 16.043 grams. And we know Avogadro says 1 mole is 6.022 times 10 to the 23rd. And it can be anything. That's why there's no unit out here. So we're going to say this is molecules. All right, equals this. So let's do this out. 35.88 divided by 16.043 times 6.022. Remember to use that EE button on your calculator there, EE23. And we should have a lot of atoms, 1.34681. I'm going to run out of room to my mole here, times 10 to the 24th. And this is molecules. Okay, if we look at our data, we need 4 significant figures here. So let's round this dude. 1.347 times 10 to the 24th molecule. Sorry, little mole. There we go. All right. Does that make sense? Do we have questions about that? You can't say that to my video, but you can email me. You can ask questions, whatever you need. See me in class. Oh, we got more. All right. Formulas as conversion factors. So 2 things to remember, right? The formula gives you how many atoms are there. Okay. And the number of atoms always relates to moles, right? So what this means is if we're talking about SF4, that this would say that one, right, we can think of it in terms of molecules. One molecule is going to have 1 sulfur atom. It's also going to have 4 fluorine atoms. Okay, because that's what our numbers there tell us. Anytime we have the word, well, we can also do this in terms of moles. So we could say 1 mole of SF4 has 1 mole of sulfur, and it has 4 moles of fluorine. Okay. We can use these coefficients to tag in and try to figure out some stuff. Okay, this works with any formula you want to do. Okay, So here's our question. How many fluorine atoms are in 8.103 grams of sulfur tetrafluoride? I've figured out the molar mass for us. So there it is. Okay, so we're looking for grams. No, we're given grams and we're looking for fluorine atoms. That means we're going to go grams SF4 to moles of SF4. The moles relate to the moles of fluorine, and then we can get to grams of fluorine. Okay, does that make sense? So let's do it. Okay, start with what we're starting with. 8.103 grams SF4. Now this one we're doing grams of different things and moles of different things. So we're going to put the formulas in there because I like the formulas in there and you need to put the formulas in there just so we know what we're talking about. All right, grams of SF4, we're getting molar mass. So 108.057 grams per 1 mole. Itch my nose, this is SF4. SF4, okay. Once we have that, we know from the previous little bit we just said that 1 mole of SF4 has 4 moles of fluorine. And we'll know that 1 mole of fluorine is, do I have a, nope, okay. 1 mole of fluorine is, sorry, I'm dawdling while I find my periodic table because I didn't put it in the slide like a good little boy. There it is, 18.998. And I went back this way, okay. 18.998. So you can always find those guys on the periodic table, which you'll always have, okay? So we got a lot of stuff going on here. We can multiply across the top, multiply across the bottom, write those down. Essentially, we only have one thing on the bottom because we have a lot of ones in here, so we can just divide it, okay? 8.103 divided by 108.057, multiply by 4, multiply by 18.998, gives us, wait, I didn't need grams of fluorine atoms. Okay, call me stupid. That's why I didn't have the fluorine thing up here. We don't want grams of fluorine. We want moles of fluorine. And I'm not going to redo this video because you guys should know that I'm going to work stuff up here. All right, so let's go back on this. 8.103 divided by 108.057 times 4. This is moles of fluorine. And I'm going to write this here so I don't have to do it again. 0.2999528 moles of fluorine. All right, and again, this isn't equal. We're counting atoms. I forgot Avogadro's number. Jeez Louise. We'll fix this. I mean, you could have figured out grams of fluorine the way I did it, but we weren't looking for grams of fluorine. We're looking for atoms of fluorine. And you can have this as proof that I am not infallible. 1 mole of fluorine is 6.022 times 10 to the 23rd fluorine atoms. Okay, there we go. Equals, I don't need this arrow there because we weren't actually looking for moles of fluorine either. Okay, let's take what we just figured out. This 299 is the first 3 bits. We'll multiply this with 6.022 times 10 to the 23rd. I'm probably not making you any more confident in my skills at this. 1.8063158 times 10 to the 23rd fluorine atoms. And I've run out of room to round this. What do we want to round it to? 4 significant figures again. I'm going to hurt our brains here. We're going to take this, I'm going to round it up here. 1.806 times 10 to the 23rd fluorine atoms. All right. You can do it. Okay. One more thing. This works with ionic compounds, and so we can do this for pretty much anything, right? And now we can do it in terms of counting ions because the mass of an ion is the same idea as the mass of the atom, because from a chemistry perspective, we're going to pretty much ignore that electrons have mass, even though it's very, 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 very small. Okay, so we have ammonium phosphate. We know it has 9.25 times 10 to the 22 ammonium ions in the sample. And we want to know what is the mass of the sample in terms of grams. We're going to need molar mass. There's molar mass. I've also given us the formula of ammonium phosphate, but you should know how to figure that out at this point. Yeah, let's just dive right into this. Okay, this will be the last thing. Good. So I'm going to plan this out better. We need ammonium. Remember, ammonium is NH4 plus. We know how many ions we have. This is going to relate to moles of NH4, which we can then get to be moles of, I should have used a shorter formula, NH4 3PO4. Okay, and then this will get to grams of ammonium phosphate. This says ammonium phosphate, just trust me. Okay. Right, we're looking for mass of the sample in grams. We're given this many. Okay, so I didn't screw this one up. Good, let's write this out. This is what we're starting with. 9.25 times 10 to the 22 NH4 plus ions. Okay. To get from ions to moles, we need Avogadro's number. So we have ions on the bottom. So we need Avogadro on the bottom, 6.022 times 10 to the 23rd NH4 plus ions. This is for 1 mole of NH4. Yes, I'm putting formulas again because we're not having the same formula throughout the whole problem. So we need to keep that in there. 1 mole of NH4. So look at our formula here, right? For 1 mole of ammonium phosphate, NH4, 3PO4. Think it through. How many moles of ammonium are there? Well, this is ammonium. There's 3 moles of this dude. So 3 moles of NH4 plus for 1 mole of that. Now we can get to grams using our molar mass, right? We're not doing anything super new, just throwing this particular one conversion factor in there and then watching me screw it up. So you guys are doing okay. Okay. 1 mole of NH4 3PO4, okay, is 149.083 grams NH4 3PO4. Awesome. All right. This one, because I'm feeling gun shy, I'm going to do it long way around. 9.25 times 10 to the 22. Remember, use the EE button to make that not be stupid. Is shit times 149.083. There it is 1.37902 times 10 to the 25th. And then we're going to do 6.022 EE23 times 3. That gives us our denominator, 1.8066 times 10 to the 24th. This has units of grams. I'll go ahead and put the formula here too, NH43PO4. Lastly, we're going to divide those two answers we just got. So this guy divided by that guy gives us 7.633221 grams. 3 significant figures because our starting ions was 3, so we'll round this to 7.63 grams NH3. Shoot. NH4 3PO4. Okay. There we go. I get a -1 because I didn't put it here either. NH4 3PO4. There we go. All right. Sorry, this one was awkward, but there you go. Love it. Have a good one. Let me know if you're stuck or need anything, and I'll catch you later.